Welcome to Industrial PLC Applications Level 2. This is a review of timers and counters. This review will focus on delay timers. After completing this series, you should be able to identify various types of timers used in programmable logic controllers. You should be able to add a timer to a connective component workbench project program. You should be able to apply the time data type with various timers, and you should be able to explain and program timer parameters. You should be able to program a TON, TOF, RTO, or a TONOFF timer. In business, time is everything. Time is money, and controlling a process is all about controlling the time that actions take place. Some of the earliest mechanical controllers were time-based. We'll begin our look by looking at on-delay timers. On a PLC, they're often called a TON, or simply a timer on delay. On-delay timers are likely the most common type of timer used. From the arming delay of your security system to alarm clocks to rockets blasting off into space, time delay applications are everywhere. With PLCs and controlling the flow of a process, an on-delay timer stalls the action of a process until a fixed time has expired. Often in PLC commentary, the period prior to execution is called the such and such delay, because that's exactly what they're trying to achieve. Getting back to our security system, when you're setting up a security alarm, there are things you need to enter to make it work. Well, first you have to arm it. Second of all, you have to have a programmed evacuation time to give yourself time to leave without tripping it yourself. 3, you have to have a trigger like a door switch or a window switch or a motion detector. And then 4, you've got to figure out what to do if the clock runs out. If someone should trip the switch after you've left, how much time do you get before the alarm goes off or it calls the security company? All of those things have to be entered into the security system. TON instructions, or on-delay timers, are no different. They have to be set up to determine what to do and when to do it. On a typical instruction, you're going to have 4 variables that you have to take care of. So the first one you want to do is look at your .in. So the name in this particular case of our timer is TON example. Fair enough. So in this example, the in is looking for something to be true. When it turns on, that's what's going to start the timer to count. As long as that in is on, it's going to count. If the in is reset, turned off in the meantime before the count is finished, shuts down and starts again. If the in stays counting, then we have to set up something to count. We have to have a predetermined time or a program time. And in this example, it would be our TON_example.pt. Now, .pt has to be constructed so that the PLC and people know what we're talking about. So they've set up a special format called a time data type that allows humans to enter a certain amount of seconds, times, minutes, hours, or days that the PLC will convert internally into a binary number that it knows what to look for and compare to. The next part of that comes with the package, which is what happens after the time has elapsed. So our TONexample.et is where that is stored. So once the in is set, it's going to start to elapse time and constantly compare it to the programmed time. Once those two agree and the input in is still true, then it turns on the output. It sets off the alarm, in which case that would be TONexample.q. And that bit will stay on just like an alarm will until somebody turns the power off on your security system and resets the button or gives the access code, or the police come in, something to turn that input off. Same thing applies here. Once the input IN is removed, then everything is reset. The elapsed time is cleared. We still have a program time, but the queue is turned off and the instruction is no longer functioning. Let's do a quick review. So, if the .in input is true, then the timer begins to time. When the .et, the elapsed time, has reached the .pt, program time, the output Q turns on. Whenever the .in input condition goes false, the timer stops, the ET is cleared, and the Q is turned off. There are a lot of applications or uses for TON timers. They're often used for time delays for sirens, like an alarm. They're often used for star delta motor starters and sequence starter delays. The TON timer is an on-delay timer, which means that its output will be delayed until a certain amount of time has expired. So on our demonstration here, we have an input waiting to turn on the TON example.in input. When that becomes true, then it looks at the program time and will start to count towards it. Once that elapsed time equals the program time, the Q bit is turned on. So turning on our timer, we can see that the elapsed time is counting up, and we've reached our 5 seconds, and the output Q has turned on our output, digital output 5. Now that will stay on as long as our TON start input is true. When it goes false, then the timer resets. If it starts to count and halfway through we lose that input, then the count time is lost as well. It does not retain the time. So just remember, with a TON timer, the .q output becomes true when the .in input to the timer is true and when .et equals .pt. This output will remain true as long as the .in bit remains true. In our next video, we're going to show you how to program a TON instruction. Until then, thanks for watching and see you next time.